Let's talk about binary cross entropy, an extremely important function in machine learning. What is it, how it works, and where to use it. The function itself looks pretty complicated and a lot is going on there, but we are going to look at every part of it step by step. So BCE, or binary cross entropy, is a loss function. It means that when you're training a machine learning model like simple logistic regression or a classifying neural network, during training the model makes predictions. Those predictions are compared to true labels. And this is done with a loss function, and it tells how bad our model is at predicting and helps the optimizer figure out how to change model parameters to make it a little bit more accurate. So bigger loss values mean worse performance, and we always try to keep it as close to zero as possible. This is what optimizers do. But binary cross entropy is a special loss function because it can be used for binary classifiers. So a model that can predict two classes. True or false, 0 or 1, cats or dogs, foreground and background. You get the idea. Have two classes, you can use binary cross entropy. Now the interesting part is how it works. When dealing with binary classification, you usually have your labels fixed, so either zeros or ones, and your predictions are usually treated as probability or confidence. That is a floating point number from 0 to 1. The closer your prediction to 1, the more you're confident that your input belongs to class 1. And having your predictions and true labels, you can use BCE loss to measure how good or bad these predictions are. We can try to get some intuition about the internal workings of BCE by looking at examples. In this video, we take a look at an image classifier where class 0 means a dog and class 1 means a cat. So let's examine a simple example where our prediction matches label perfectly. The model predicts 0 and the label is also 0. Our model predicts a probability or confidence that is 0, and the true label is also 0 or dog. So the model is absolutely correct. Here's the formula. We plug y equals 0 and p equals 0, and now 0 times log 0 mathematically limits to 0, so it disappears. The other log is log 1, which is also 0. Negate the sum and we still have 0. The bottom line here is that for a perfect prediction, the loss equals 0. There is no penalty. The same happens when the model is confident with class 1 or cat prediction and it is correct. So we basically flip the situation. The model predicts a probability of 1 and the label is also 1. So the same formula, but now y equals to 1 and p equals to 1. And log of 1 is of course 0, and the second term vanishes because it's multiplied by 0. The perfect hit for the positive class, and again the loss is 0. So think of these two cases as the sweet spots at either end of the probability axis. Nothing to penalize, everything works perfectly. But if our model is a bit unsure, the error value starts increasing. So the more unsure our model is, the larger the error we get. And if the algorithm is very, very confident in the wrong choice, the BCE value grows rapidly. So let's dial back that confidence. The model is, let's say, 70% sure the image is a cat. So P is now 0.7 and the label says it is a cat. So Y is still 1. So let's see the arithmetic, and the loss now is about 0.36. So not huge, but if calculated during training, the algorithm is being told that there are some ways to improve. Let's slide a little further in the wrong direction, and the model is now only 30% sure. So it actually leans toward not a cat or a dog, a negative class, and the label is still 1. So we compute the loss, and now it almost triples to 0.92, signaling some more serious mistakes. And now imagine the model shouts, It's definitely a cat with 99% certainty, but the label is 0, so it's a dog. So plug in y equals 0 and p equals 0.99, and we get 4.6. So that's order of magnitude bigger than any previous loss. We can see this effect in this plot. So the orange curve where y equals to 1, or our label is 1 or a cat, drops steeply as p moves from 0 to 1, hitting 0 at perfect certainty. And the red curve mirrors it, and this belongs to the case where y equals to 0. It drops to 0 as p goes to 0. And these both curves shoot upward near the wrong extreme, visualizing that confident and wrong scenario we just computed. And the smooth bowl shape between shows how uncertainty yields an intermediate loss. Now, libraries like PyTorch or TensorFlow have this function implemented, but let's make it from scratch at first to really get the idea, and then we can compare with versions from specific libraries. For this example, let's use NumPy and define two NumPy arrays for predictions and for labels. We define our function that will accept our arrays, but also additional parameter epsilon. This is so small, it hardly has any influence, but it helps with stability. So if you don't use it, we might run into a problem as np log 0 returns negative infinity. So epsilon will keep our log safe as we clip our values with this line, which forces every element of ypred into the closed interval from epsilon to 1 minus epsilon. We write our formula, and as we have more than one sample, we calculate the mean of our errors to get the final BCE value. We can do the same with PyTorch, but at first we have to turn our arrays into torch tensors. And we can use the BCE loss function. We can see that we get the same value. I encourage you to play with these values to gain a little bit more intuition. So for example, what happens when half of the predictions are correct and the other half are not? What happens then? The model always predicts 0.5 and so on. However, now you understand the internals of binary cross entropy loss. It is a great function, usually the first thing people try with binary classifiers and usually the one that does the job. So I hope you find this video useful. Hit the like button and consider subscribing if you do. And I'll see you in the next one.